We're in Unit 5, Introduction to Functions, Lessons 7 and 8. Using graphs to find rate of change and interpreting and creating graphs. Our learning targets for today are: I can estimate or calculate the average rate of change between 2 points, either given 2 points or finding 2 points from a graph. I can explain the meaning of the term average rate of change. I can sketch a graph that shows important features of a situation. So we're talking about a word problem. We're going to relate what we know to a word problem and then make sense of important features of a graph and explain what they mean in a situation. Turn to page 70, pause the video and work on this bridge. When you have had a chance to answer all 4 questions, come back and compare your answers with mine. All right, the bridge says a function assigns the inputs shown in the corresponding outputs in the given table. So we have a table, a horizontal table, a vertical table with the input and the output. So your x value is going to be the input. X is always the input. The y value is going to be always the output or the answer. Question number 1. Do you suspect the function is linear? Compute the rate of change of this data for at least 3 pairs of inputs and their corresponding outputs. All right, so let's look at our x values. We have 1, 2, 4, and 6. So we've skipped 3 and we've skipped 5. So let's look at what happens between 1 and 2. Look at the y values. We go from 2 to negative 1. Take a minute to think about what's happening. How do you get from 2 to negative 1? Do you add, subtract, multiply, divide? And then let's test it to see if whatever you think is happening continues to happen between any 2 set of points. All right, to go from 2 to negative 1, sketch a number line in your workbook. All right, here's 0, 1, 2, and then 0, we're going to go to the left, to negative 1, negative 2, and so forth. We can add on more points if we need to, but I'm just trying to see what happens to get from 2 to negative 1. So I'm going in reverse, 1, 2, 3. So that means I'm subtracting, it looks like I'm subtracting 3. All right, so 2 minus 3. Change your subtraction to addition of the opposite. Whatever is following it, change it to its opposite sign. So 2 take away 3, or 2 plus negative 3, is negative 1. Now let's see if we can carry that down and get the point for 3. Let's go ahead and add that row in there. All right, negative 1. What are we adding? We're adding negative 3. You can also consider this as subtracting 3. So negative 1 plus a negative 3. Here's negative 1. Then we're going to go backward. Negative 2. It's 1, 2, 3. So we're going to end up at negative 4. Okay, so we skipped 3, but I'm going to put that row in there. 3, negative 4. Now let's keep using that rule of adding a negative 3. So plus negative 3. You can also think of it as subtracting 3. Negative 4 plus negative 3 is negative 7, so that checks. All right, now we missed 5, so let's put that row in there. All right, negative 7 plus a negative 3, or subtract 3, gives you negative 10. And now we can go from 5 to 6, just going up 1 each time. So negative 10 minus 3, or negative 10 plus a negative 3, is negative 13. Okay. So the rate of change is, what do you think the rate of change is? What are we changing by each time? Okay, we're changing by negative 3. All right, let's look at this example, and let's look at the work. Write this down in your workbook on page 70. We're going to find the difference. Let me just go ahead and subtract all this, erase all this. All right, the rate of change we compute by taking any 2 points. I put those numbers that we were missing in between just so you could follow along. But we don't have to have the missing points. We're going to start with these 2 points, the first 2. And we're going to find the rate of change. So this looks like we're starting with the y's. 2, take away negative 1. So we're finding, it looks like we're finding the slope, rise over run. All right, and then we take the x values, 1 minus 2. All right, 2, take away a negative 1, change the subtraction to addition of the opposite. 2 plus 1 is 3. And then 1 minus 2 would be 1 plus a negative 2 would be negative 1. So that's going to be negative 3. So that's what we looked at. That's what we tested out. Our rate of change is our slope. All right, now you take any 2 points and calculate the rate of change. In other words, find the slope. So I'm going to take the next 2 points. 2 and 4 are, or actually I'm looking at it again. We're taking 7 and negative 13. We're taking those last 2 points. All right, and 4 and 6. So let's start with the y values. All right, I'm going to start with 7 and subtract negative 13, and that becomes plus a positive 13. Negative 7 plus positive 13 is positive 6. All right, now we're going to go back to these 2 points. Start with the same point each time. So I'm going to start with 4 for the x values. 4, take away 6. That becomes 4 plus negative 6. 4 plus negative 6 is negative 2. Use your calculator, use your brain, however you do this, simplify this. 6 divided by negative 2 is negative 3. So that checks out. We have the same rate of change. In other words, we have the same slope. All right, now pick any 2 points. Let me erase some of this work that we've done over here. Any 2 points that we haven't used so far. Doesn't matter what you've chosen. I've chosen 1, 2, and negative 4, 7. So I'm going to choose the first point and the third point. Okay, and I'm going to start with the y values. 2 minus negative 7. That is going to be 2 plus 7, or 9. And then let's go back to our x values. I'm going to start with 1 and then subtract 4. So 1 plus a negative 4 is negative 3. Simplify this and you get negative 3. So we have a constant rate of change. Okay, to go up 1 each time, we're going to get negative 3. That's what we're changing for each increment of 1. Okay, since the rate of change is the same, I know it's a linear function. Make sure that you have those notes copied down in your book. So pause the video, fill in anything that you might be missing. And let's go on to the second question. Question number 2. Which equation seems to describe the function? or what equation seems to describe the function. All right, we have our slope, but we don't have our intercept. So let's go back to our equation y equal mx plus b. Okay, we said our rate of change is -3, so we're going to substitute that in for the slope, but we don't have our intercept. So our intercept, we know when x is 0, we're going to find where we cross the y-axis. Okay, so you can put in any point for your x and y. You can substitute in your slope, and you can solve for b. So let's just choose that first one. We'll choose 1. 1 is x. Slope is -3. And our y for that first point is 2. So 2 equals -3 times 1 plus b. Okay, -3 times 1 is just -3. Okay, now we're going to solve for b, so I'm going to add 3 to both sides. Three plus 2 is 5. That doesn't really look like a 3. This is going to be 0, so 5 equals b. So when x is 0, y equals 5. Let's see if that works. Now going forward, we're subtracting 3. So in reverse, what do you think we would do if we go backward? What's the opposite of subtract 3? We're going to be adding 3 to get to 0, from 1 to 0. So 2 plus 3 is 5. So that does check out. All right, I've made a mess of this down here, so let me just write this up here. Y equal, the slope is -3, x plus the y-intercept is 5. All right, so I'm showing the work here a little bit neater, where we plugged in a point. They chose 2 for y and 1 for x, so they chose that first point. Okay, and then solve for b. That's what we did. Okay, and then we put it into the equation y equals mx plus b, because we've already calculated the slope. We just had to find the y-intercept. Now, as you did not verify that the rate of change is constant across all input-output pairs, check that the equation you found in problem 1 does indeed produce the correct output for each of the following 4 inputs: 1, 2, 4, and 6. In other words, from that table, let me erase this, get it out of your way. From that table, we're going to substitute in our x and our y's and see if we get a true statement. Okay, we skipped this one here. You can skip it if you want, but I want you just to try 1. So let's try 4 and -7. All right, so we're going to put it into this equation here. Put in your x value, which is 4, right here, and substitute in your y value, which is -7, right here. So let me move down here. -7 equal -3 times 4 plus 5. -3 times 4 is -12. And -12 plus 5 is -7. I'm just working on the left-hand side. Let me move over here. Write your equal. And on the left-hand side, we had -7 already. Sorry, I'm working on the right-hand side to simplify it, compare it to the left-hand side. All right, so that is a true statement. So that's what question number 3 wanted you to do. All right, you would do that for all 4 of those, but just do one, write down one example. You can take any of those points and you should get a true statement. All right, what will the graph of the function look like? Explain in words. Now we've been looking at linear functions. Okay, and so we should be able to talk about them. It's not brand new. Now, you can have a different answer than mine. I said the graph of the function will be aligned through the points given in the table. You could also say something like this graph goes through the y-axis at 5, and it has a slope of -3. So it's going to slant to the left. Something that you've learned so far to describe what the function looks like. So there could be a variety of answers. I can tell when you're going and searching for questions and copying answers from the internet or just copying my sample answers that I give you. Try to do some thinking on your own. Okay, if you get stuck, it's okay to look, but don't always copy answers. All right, temperature drop. Let's do the warm-up. Turn to page 71. Here are the recorded temperatures at 3 different times on a winter evening. Tyler says the temperature dropped faster between 4 and 6 p.m. Mai says the temperature dropped faster between 6 p.m. and 10 p.m. Who do you agree with? Explain your reasoning. Pause the video now and then come back to it and compare answers. All right, let's look at what happens between 4 and 6 p.m. Remember, this is your X, this is your input, and this is your Y, output. Time is always input. Y is always output. X is always your independent variable, and Y is always your dependent variable. Okay, so let's look at what happens between 4 and 6. How many hours between 4 and 6? And what is the temperature change between 25 and 17? All right, so let's start with our Y's. Okay, I'm going to start with 25, and I'm going to subtract 17. And I'm going to put that over the difference in my X's, but make sure you go back to the same point each time. So I'm starting here at 25. I'm going to start here at 4. 4 minus 6 equal. All right, 25 minus 17 is 8. And 4 minus 6, change this to plus a negative. Okay, opposites subtract. So 6 minus 4 is 2. You're going to take the sign of the larger absolute value. 6 is bigger than 4, so we're going to take that negative. 8 divided by -2 is -4. Okay, now let's find the rate of change between 6 and 10. Okay, we tested what the rate of change is for Tyler, and that's -4. Let's find the rate of change between 6 and 10. So start with your Y values. 17 minus 8 over, go to your X values, start with the same point, 6, take away 10. Seventeen minus 8 is 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 is 9. And 6 minus 10 is -4. Okay, so the rate of change here between 6 and 10 is 9 over -4. Put that in your calculator, you get -2.25. All right, check using your calculator. All right, so the rate of change is it more or less here? We're dropping by 2.25 between 6 and 10. My says the temperature dropped faster between 6 and 10. So who do you agree with now? Which one dropped more rapidly? All right, I agree with my. The temperature dropped 8 degrees Fahrenheit between 4 and 6 p.m., but it fell 9 degrees Fahrenheit between 6 and 10 p.m. I agree with Tyler. The temperature dropped 4 degrees per hour between 4 p.m. and 6 p.m. It fell less than 4 degrees Fahrenheit per hour in the evening. All right, so it's just what you see, but the correct answer is it's decreasing less between 6 and 10 p.m. This is a smaller number, a, a smaller absolute value than -4. So it's decreasing more rapidly between 4 and 6. I'm going to agree with Tyler. All right, but this is a chance for you to think. Get in the practice of writing your answers in complete sentence, and then talk with your group to try to figure out how that question is answered and how to look at it to get the correct answer. On page 72, activity 1, we have a table and graphs. So we have a table, so here's our X and here's our Y, and then we have a graph that shows a more complete picture of the temperature changes on the same winter day. So we've graphed those points. The function T gives the temperature in degrees Fahrenheit, H hours since noon. Find the average rate of change for the following intervals. Explain or show your reasoning. So we're looking between noon and 1 p.m. Okay, so noon is going to be at 0. Okay, we start at noon. The next hour is going to be 1 p.m. Okay, you can look at the graph, but I like to look at the table, noon and 1 p.m. Now let's find our slope. So I'm going to start here with the second point, 19 minus 18 over 1 minus 0, which is just 1. 19 minus 18 is 1, and 1 over 1 is 1. So the rate of change here is 1 between noon and 1 p.m. Okay, so 1 degree per hour. The temperature is dropping 1 degree per hour. I'm sorry, it's rising because that's a positive one, not dropping. Also, you can see from the graph it's going up between noon and 4 p.m. So we're going to go from 0 to 4. Okay, so find the rate of change. Let me erase this here. Noon is going to be our starting point, so that's 0 to 4. So 18 minus 25 over 0 minus 4. All right, 18 minus 25 is -7 over -4. I think that's correct. Get your calculator out and check. Okay, 2 negatives, you divide a negative by a negative, you get a positive. So that's positive 7 over 4. Okay, the temperature increased by 7 degrees in 4 hours. The average increase, go ahead and divide 7 by 4, is 1.75. So it's increasing more rapidly between noon and 4. You can see a rapid increase right here. Okay, between noon and midnight. So we're going to go from 0 to 12. So let's start at 0, going back to noon. Okay, and we're going to go up to 12. So 18 minus 7 over 0 minus 12. 18 minus 7 is 11. 0 minus 12 is negative 12. So simplifying that, we get negative 11 over 12. Okay. So the slope connecting the 2 points, these 2 points, we're not looking at all of them, just this point and this point is negative 11 over 12. So let me show you what I mean by that. Let me just go ahead and draw those lines. Okay, this is the one that we just did. Okay, between noon and 4, we're connecting these dots. Is that correct? Oops, I got to go up a little bit. All right, let me undo that. That didn't connect quite right. Okay, and then between noon and 1, that would be this right here. So they're all going to be a little bit different. Just make sure that you know how to find the slope, which is also the rate of change between 2 points. We're looking at and graphing linear functions. Remember my and Tyler's disagreement? Use an average rate of change to show which time period 4 to 6 or 6 to 10 experienced a faster temperature drop. Now I think we've already answered this. Let's go ahead and get this written down. All right, the temperature dropped faster between 4 and 6 p.m. because in the first interval we can find the rate of change, which is 4. In the second, the rate of change is 2.25. Over what interval did the temperature decrease? Let me move this over a little bit so you can see it. Decrease the most rapidly. Okay, looking at the graph or calculating it from the table, between 5 and 6 p.m., right here, between 5 and 6, here's 5, here's 6. Look how quickly it drops down. You can also verify that by finding the slope between 5 and 6. Over what interval did the temperature increase most rapidly? So we have to find a point and then another point immediately following in that interval that goes up. So between 3, I can see it right here, between 3 and 4, that's when it goes up most rapidly. And you can also go here to the table and calculate the slope. Activity 2, populations of 2 states. We have a graph that shows the population in California and Texas over time. So the blue line is California. California starts below Texas, which is the dotted red line. Okay, but in about year 1930, California starts matching the population of Texas, and then it rapidly increases. Estimate the average rate of change in the population in each state between 1970 and 2010. So let's go to 1970 and 2010. The population of California in 1970, okay, so go up to the blue line, was about 20 million. And in 2010, it was about 37 million. So this is where you have to kind of estimate. I say 37, maybe you said 38. Okay, and then the average rate of change is, take those points. Those points would be 1970, 20, we're talking about millions. And then the second point is 2010, 37. Okay, find the slope. Rise over run. So subtract your y's, subtract your x's, and you should get 0.425 million per year. The population of Texas was 11 million in 1970, so we can go to 1970 and go up a little bit above 10 over here. to 11. Okay, so we have those 2 points, 1970 and 11. Okay, so write those down. And then in 2010, it looks to be about, what does it look like to you? 2010, let's say 25 million. Yep, that's what they've got down here. So the average rate of change, start with your Y's, 25 minus 11. It might be easier to write those points down too. 1970, comma, 11. You get the idea. And then 2010, 37. And then you can find the slope. Okay, calculate the slope and you'll get 0.35 million per year. Now look at that question. You found the answer to that question. What does that mean? What does each rate of change mean? On average, the population in California was growing by 425 million people per year, and the population of Texas was growing by 350,000. I said million, 425,000. Texas, 350,000, because we're talking about millions. So we take that number, let's just take 0.35, and we've got to move this over 6 places. A million has 6 zeros. 1, 2, 3, 4, 5, 6. Fill in the zeros. There's no decimal left anymore, and put in your commas. So that's how they get that 350,000 and 425,000. Now, which state's population grew more quickly between 1900 and 2000? So we're going to go to 1900, which is right here. Okay, and we're going to write those 2 points down for California and for Texas. So let's start with California. Let's start with the blue line. So the year is 1900. That's going to be our X. And our Y value for 1900, let's look at the blue line. Where do you think that is? It says California is growing more quickly. Maybe we didn't have to look at the slope, but we could. You can look at the line and see and kind of estimate which one is increasing more quickly. Okay, but you can also do it with slope. 1900, that looks like about not 10 million, but 1 million. 1 with 6 zeros. 1, 2, 3, 4, 5, 6. You can use scientific notation if you want to. Okay, and then 2000, we're looking at California. We already have those 2 points. Oops, no we don't. That's 2010. 2000 is going to go up to about 30, not quite 35, 34 million. And then you can calculate the rate of change. You can do the same thing for Texas for those 2 points. But I would, if I'm estimating, I'm probably just going to look at the graph to see which one's increasing most rapidly. Don't forget how to find rate of change. That's finding the slope. All right, complete the cool down in Canvas. Make sure that you look at your notes and that you try to use what you've been learning in this lesson to complete the cool down and give me some feedback. Turn to page 80 and let's complete the bridge. We have several lines. I want you to match each line shown with the slope. So those little triangles, those right triangles, are there to help you find the slope. Remember, rise over run. Going up is positive, going down is negative. Going left is negative for the X direction, and going right is positive. Okay, so that should help you quickly find the slope of each line. For the ones that do not have the right triangles drawn, you can draw a right triangle. Just make sure that you connect to 2 points that you know are there. Calculate the slope. All right, so let's look at the first one, and the rise is 3. Okay, starting here, but we're going down. So that's going to be a negative 3. And then we go back in a negative direction, negative 2. A negative divided by a negative is a positive, so this is positive 3 over 2. Let's look at B. We're going to start here at this point, and we're going to go down 2, so that's down is negative, and then to the left, 1, 2, 3, 4, 5, 6. Negative 6. A negative divided by a negative is a positive. 2 divided by 2 is 1, and 6 divided by 2 is 3. So this is positive 1/3. So that's going to be this one right here. All right, let's go to C. We're going to go down 1, 2, 3, 4, 5. So that's negative 5. And then to the left, 1, 2, 3, 4, 5. 5 divided by 5 is 1. A negative divided by a negative is a positive. So here we match up with negative 1. All right, now let's go to this one. Pick any point, and we're going to go down 1, 2, went down 2, and then to the left, 1. That's also negative. Negative divided by a negative is a positive, so that slope is a positive 2. All right, pick any point on the line that you can see clearly. So I see this point here. We're looking for a line or point that lines up on that graph right there. Those lines, those intersecting lines. And then we're going to count down 1, so that's negative 1, over, go to the left 3, 1, 2, 3, one more, 4, so that's negative 4. A negative divided by a negative is a positive, 1/4. Because you could also start here and go up 1 and then over 4. Okay, that would give you two positive numbers. 1 divided by 4 is 0.25. 1/4 or 0.25. And then C is not here. It should be in your book. I don't know why it didn't come out. Should give you 1/2. All right, one of the slopes does not have a line to match. Draw, that's this one. So draw a line with the slope of 1/2. So to do that, I'm just going to start on any point. I'm going to rise 1. We rise first, and then I'm going to run 2. So that's a slope of 1/2, and then connect those dots. Yours may not look exactly like mine, okay, but it has a slope of 1/2. All right, do the warm-up on page 81. Which one does not belong? Okay, explain your reasoning. So I'm just going to go through this. You can pause right now, but I'm going to go through this when you come back really quickly. You can reason that any of these don't belong. Okay, I say graph A doesn't belong because it's the only graph that has no maximum or minimum. It's just straight across. Okay, the temperature does not change. It just stays constant. Okay, you can also say B doesn't belong because it's the only graph that has horizontal intercepts. So it crosses the x-axis. Those are horizontal intercepts. 2 places, here and here. Okay, it has negative output values or negative temperatures. That means it goes below the x-axis. It's the only graph that shows temperature falling and then rising, but it doesn't fall again. So there are different things that you can notice that you can say about graph B. Okay, graph C. If you reason that that one doesn't belong, you can say it's because the graph only has one maximum. So we're talking about the vocabulary of maximum and minimum. Okay, graph A doesn't have a maximum or a minimum. It doesn't change at all. But graph C it does have a maximum, but only one. D has two maximums or peaks and one minimum. Okay, it shows, let's go back to graph C. It's the only graph that shows the temperature rising and then falling, but not rising again. Okay, graph D, you can reason that it doesn't belong because it's the only graph that has several maximum and minimum. So it goes up, it goes down, it goes up, and it goes down. So it has a multiple number of maxima and minima. Okay, it shows the temperature rising and falling, rising and falling. It shows a repeating pattern as well. So you can notice different things. This isn't all, but it's just a part of the thinking process. Turn to page 82 and complete activity number 1. Now let's look at this and understand what the problem is saying. We have a flag ceremony held at a 4th of July event. The height of the flag is a function of time. Now here are some graphs that could be possible representations of the function. For each graph assigned to you, normally if we do this in class, I assign everybody a different graph. But let's just go through all of these. Let's look at the graph for A. Can you explain what it tells us about the flag? So we're looking at time. Where do we start on the x-axis? Okay, on the x-axis we're going to start at noon or at 12. I really don't know whether it's noon or midnight, but I'm going to assume it's noon. Then at 1, okay, here's where the flag is. At 2, here's where the flag is, and so forth. So what's happening is the flag is being raised at a constant rate. Maybe 1, 2, 3, 4, 5, 6 is in terms of minutes. Okay, it's not explicit enough. It doesn't explain that here. But this is time. Time is always going to be our x value, and our output is going to be height. All right, for graph B, when we start, the flag is not on the ground. It's at 3 feet, and it stays constant. The entire time it stays at 3 feet. For graph C, the flag starts on the ground. It rises, okay, and then it kind of evens off, and then it starts rising again at 3 minutes. The flag starts out quickly but gets pulled up quickly. Then the movement slows down and there's a brief pause, and then it's raised up again at a quicker rate. Can you explain what's happening with D? Flag is going to start on the ground, raised up quickly, and then it drops down. Raises up, drops down. This is a constant pattern where it goes up and then down. For E, we don't start on the ground. We start at about half a foot, 0.5 meters, measuring in meters. And it's raised up bit by bit, and it seems to be a constant pattern where we raise it up rapidly, rest, raise it, rest, raise it, rest, raise it, rest, raise it, rest. Okay, a brief pause before it's raised up further. Okay, and the last one, the flag starts on the ground, it's raised up at a constant speed for 3 seconds, it stops abruptly, and then 2 seconds later, from 3 to 5, okay, it goes down, it stops at 3 meters, and then it stays that way. Okay, so practice looking at the question, understanding what that graph is telling us, focusing on maximum, minimum, rate of change. Now decide as a group which graphs appear to be most realistic and which ones are least realistic. So pause and take some time to talk to someone in your group who is where you are and talk it over, which one's most realistic, which one's least. and then answer in your workbook. All right, some sample answers, no right or wrong. Graph E seems most realistic for some people because if it's a person pulling up the flag, they're not going to start on the ground. They're going to start about halfway, about a meter above the ground, pull it up, and then they're going to rest, pull it up again. So it's kind of a jerking pattern of pulling and resting. Okay, graphs B and D are the least realistic because when we're raising a flag, we don't just stay at 3 feet. Or we don't raise it up and then drop it and then raise it and drop it, raise it and drop it. Okay, graphs A and C and F are possible, but they're unlikely. A, if a machine is doing the pulling, it could have a constant rate. Okay, but it's unlikely because the flag starts on the ground. And if you know anything about flags, we don't like our flags to touch the ground. Okay, this last one, it goes up quickly, drops down, and stays constant. So those are unlikely, but they could happen. These two are the least realistic. Okay, question number 2. Here's another graph that relates time and height. Can this graph represent the time and height of the flag? Okay, the time is at 3 minutes. I guess it's minutes. And then the height, it just keeps going up and up and up. Pause here, explain your reasoning, write something down, and then come back and compare your answer to my answer. I'm not saying my answers are correct. I'm just going to give you a sample answer. And then, is this a graph of a function? Explain your reasoning. So we've been talking about functions, what makes a function. You should be able to explain this answer just by looking at your graph. All right, you're back. Question number A. No, the graph shows the flag being at all heights at the same time, between 0 and 6 meters at 3 seconds of time. So how can the flag be at different heights at 3 seconds? That's not possible. It is not a function because it doesn't pass the vertical line test. If you draw a vertical line, let's go ahead and draw one, and then move that vertical line through the graph. All right, let me grab it. I'm having trouble grabbing it. Well, you see what I mean. It's going to lay on all those points. It's going to touch in more than one place. So no, it's not a graph of a function. A function has only one output for every input. And this graph shows many possible outputs when the input is 3. All right, go to your glossary and summary on page 89. Go through the glossary and the summary for both lessons. Make sure you're reading through that, highlighting. I'm going to be doing a workbook check probably on Friday. Go through the summary and glossary, take notes, complete both cool downs, and complete the practice problems on page 75, 1, 2, 3, and 7, and on page 90, 2, 3, 4, and 5.